Let the verifications begin. All right, so trig verifications usually end up being students' least favorite and most thought-provoking exercises out of all of trigonometry. And that is because when you see an equation, you already know it's true. You're asked to basically verify that cosine of theta times this binomial equals 1 minus sine of theta. Okay, so how do you do that? Well, what you need to do first step is to make sure that you're only working with the more complicated looking side. So here I have cosine of theta times secant theta minus tangent theta equals 1 minus sine theta. There's definitely more happening, more to work with, and hence more complicated on the left-hand side. So what does that mean for you? That means you need to write your goal down here. So my goal is to manipulate this left side so that I get 1 minus sine of theta. We're basically proving that this left side equals this right side. And all of the work that you're going to show here is the proof, and therefore is your solution for this type of exercise. So the first thing I think I want to do here is to multiply cosine times both of these things and get cosine theta times secant theta minus cosine theta times tangent theta. And so while I'm working through this example, I am not going to use the right side of this equation at all. I'm going to scribble it out. I've already written it down here, and this is my goal. So what I'm going to do now is start looking at how cosine interacts with secant and how cosine interacts with tangent. And I'm going to do that by rewriting everything that is not a secant or everything that's not a cosine or a sine in terms of cosine and sine. So I'm going to write secant in terms of cosine or sine and tangents in terms of cosine or sine. Here's how this is going to look. So secant can be rewritten as 1 over cosine, and tangent can be rewritten as sine over cosine. And that's fine, but now look at when this happens, you can rewrite this cosine as cosine over 1, and these cosines reduce away. And we're left with a 1 here. This minus sine is still here. But in this second one, we have this cosine. You can write that one over 1. And these cosines reduce the exact same way, leaving you with a sine of theta, which is exactly what we're looking for. We're looking for that 1 minus sine theta. So all of this work right here is the solution to prove that cosine of theta times the quantity secant theta minus tangent theta is equal to 1 minus sine of theta. And so I'm going to do something very similar over here for this one. Cotangent theta over cosecant theta equals cosine theta. Anytime I see a fraction, I know that is definitely more complicated than not a fraction. So over here, I don't know how this cotangent and cosecant are going to interact with each other. So I'm just going to rewrite cotangent and cosecant in terms of sines and cosines. And this is going to end up something like this. Cotangent is cosine theta over sine theta. So that takes care of this portion. There we go. The white box goes to the white fraction. And then in this one, cosecant turns into 1 over sine theta. And what's my goal here? My goal here is to get cosine of theta. So I know this does not even matter. That's not on my radar anymore. I'm not even going to consider that. So anytime you have a fraction within a fraction, here I have a fraction in the top of a fraction and a fraction in the bottom of a fraction, I want to find the LCD of these little fractions. In this case, it's just going to be sine of theta. And the whole point of finding the LCD is to multiply the big fraction by that LCD. And again, the whole point in multiplying the LCD is to get rid of these fractions. So this leaves me with a cosine theta over 1, which is just the same thing as cosine theta. So that's it. This is all the proof we need right here to show that cotangent theta over cosecant theta is the same thing as cosine theta. So on this slide, a couple more examples of how verifications work. Now, one thing that you're going to come across within verifications is that it is easier to turn a side of the equation with two terms, like cosine theta, and the second term being sine theta tangent theta. It's easier to turn two terms into one than it is to turn one into two. So this leads me to believe that I'm going to want to write the secant theta way down here. So now this equals secant theta is off my radar. I'm trying to rewrite cosine theta plus sine theta tangent theta as a secant theta. Well, let's see how this is going to work. I think the first step here, I want to rewrite everything in terms of sines and cosines. So this will be sine theta plus cosine theta, sine theta over cosine theta. Awesome. So now what I'm going to do is combine these together to get this. I just multiplied the two sines together. You could think of this sine as being over 1. You multiply the numerators together, and you multiply the denominators together. So from here, I can't very well turn this into one term unless I have a common denominator. So I can't turn two terms into one if I don't have a common denominator. So what I'm going to do is multiply just this term by cosine of theta over cosine of theta. So the rest of this will look like this: cosine theta plus sine squared theta over cosine theta. And so now by doing that, I have a common denominator. I've got a cosine in this denominator and a cosine in this denominator. Don't go canceling these. You're doing this so that you have a cosine in each denominator. So when you consider this cosine being over 1, you end up with a new expression: cosine squared theta over cosine theta plus sine squared theta over cosine theta. Now that these have the same denominator, we can add these two fractions together to get cosine squared theta plus sine squared theta all over cosine theta. So I should have been putting equal signs here the whole time. Equals, okay. So now the very last thing I want to mention here is that cosine squared theta plus sine squared theta does in fact equal 1 by a Pythagorean identity. So this gives us 1 over cosine theta, which is secant theta. So this one required a little more work, as you can see. But with this idea here that it's easier to combine two terms together into one, and you will most likely be doing that by finding a common denominator and multiplying that term by the common denominator in the top and the bottom. That way you can have that common denominator. Now with this other one over here on the right, there is no need to find a common denominator to combine two terms together. But we still will be working with a common denominator in this exercise, just in a different respect. So I'm going to say clearly this left side looks much more complicated than this right side. And so with that, I'm going to put down here, my goal is to get to tangent theta. and it's like I'm not even working with this anymore. So lots of tangents, cosecants, and secants going on here. I don't like any of that. I'm going to rewrite them using sines and cosines. It'll look like this. So here's everything parsed out in terms of sines and cosines. And a tangent squared, well, first of all, tangent is sine over cosine, but if it's squared, then the sine and cosine each get squared. Cosecant is 1 over sine, secant is 1 over cosine. Now, you might want to start with something like, oh my goodness, there's a cosine squared here and a sine and a cosine in this little denominator, and I want to multiply everything by cosine squared sine. Well, before you get all jumpy and trying to find an LCD here of these little fractions, you may also want to notice before any of that a sine will cancel here. So I can cancel one sine here and this sine here. That leaves me with this. Sine over cosine squared all over 1 over cosine squared. Now, in that simplification, we don't need a sine in our LCD anymore. So what I'm going to do is multiply by cosine squared theta over cosine squared theta, just to get rid of these denominators. So in the top, that cosine squared in the bottom reduces away. In the bottom, I can only take away one of those cosines there. So this leaves me with a sine theta in the top and a cosine theta in the bottom, which is tangent. So again, all of this work here in this bubble is what you need in order to successfully verify that tangent squared theta cosecant theta secant over secant theta is the same thing as tangent theta. On this page, some reference angles. Just so you know, the reference angles are going to be within 90 degrees of a multiple of either 180 degrees or pi. So, layman's terms, if you know where an angle is, so let's say here, I know this angle, let's call it 130 degrees. Well, I know that angle is in the second quadrant, so if I were going to make a triangle out of this, I would go down to the x-axis, so I would have my right angle. And what we're interested in then is what angle is made up by that particular radius and the x-axis. And in this case, it would be 50 degrees. So, how can we start figuring this out for these first 3 angles here? Well, I don't know what 623 degrees looks like. I don't know where that is on my coordinate plane, but if I find a coterminal angle, I can figure out where that is. So let me see here. This to find a coterminal angle, I'm going to subtract 360 degrees and get 263 degrees. That way I know exactly where this angle lies. So, over here, off to the right, I'm going to draw another little diagram here, just so that you can see a picture of this. 263 degrees is between 180 and 270 degrees, maybe something like that. The question is, what is the angle that is made by the radius and the x-axis here? Well, if this is 263 degrees, that's like asking how far past the x-axis did we go here? Well, that means we just have to do a simple subtraction. So 263 degrees minus 180 gives you 83 degrees. So the reference angle for 623 is 83 degrees. And you can do something similar here with the 127 degrees. That's really close to 130. To complete that half revolution, the reference angle would need to be 53 degrees. And finally, this negative 49 degrees here. Negative 49, that would be something like this. I want to find a coterminal angle that is within the first 360 degrees. I don't want something that's bigger than 360 degrees. That's why I subtracted 360 here to find a coterminal angle. This is between 0 and 360, so I was just able to figure out how far do I need to go to get to the full 180 degrees. But this one, I want to add 360 degrees and get 311. So really this is 311 degrees. How far do you need to go to get to the full 360? Well, it ends up being 49 degrees is your reference angle here. So again, reference angles are always between 0 and 90 degrees. And if you have something that's less than 0 or bigger than 360, take it back to that first revolution so that you can more easily find the reference angle. Now for radians. With radians, we don't want anything that's bigger than 2 pi, and we definitely don't want a negative angle. So down here, we want this angle to be between 0 and pi over 2. Reference angles always happen within the first, or always located within the first quadrant. So, let's see here. And with this, right, our goal was to always go back to the x-axis. So the x-axis measures here are either going to be 0, pi, or 2 pi. So for example, if we start with this one, 6 pi over 5, well, 6 pi over 5 is bigger than 1 pi, so that would be this angle right here. All of this. 6 pi over 5. Well, we went past the x-axis, so the question becomes, how big is this angle? Well, if we just subtract, where is it? Here we go. 6 pi over 5 minus pi, you will get a reference angle of pi over 5. That's how far past this angle is. That little angle right there is pi over 5. If you add that little angle to the pi radians already, you will get 6 pi over 5. All right, for these last two, 5 pi over 9 is about right there. If you draw back to the x-axis, we need to figure out how much more pi do we need there to have a whole pi. So this is 5, wow, there we go, 5 pi over 9. So to complete over to a full pi, we just need to do a simple subtraction, the bigger minus the smaller. So this would be equal to, the reference angle for 5 pi over 9 would be equal to 4 pi over 9, because 5 pi and 4 pi equal 9 pi, but when you divide it by 9, that's how you get the whole pi we're looking for. And lastly, 11 pi over 6 means we go 11 pi over 6 in the wrong direction, and that puts you in the first quadrant. This is negative 11 pi over 6, but that value is negative. I would like to add 2 pi to this to make sure that I am within the first revolution. And when you add 2 pi, you end up with pi over 6. That is in the first quadrant. That is the reference angle for negative 11 pi over 6. On this slide, to start wrapping up the review for this particular unit in Precal, we are asked to approximate to 1 decimal place in degrees all of these equations here. So what's happening here is you're trying to figure out which theta will give you a sine value of 0.8225. Well, I promise you it's not going to be any of the nice ones that we know, pi over 6, pi over 4, pi over 3, pi over 2, or any angles in any other quadrant. Those are not it. So you will need a calculator for this one. And what will end up happening is we are trying to get theta out of the sine. All right, and you've seen examples like this before in a previous class, maybe something down here at the bottom like this, x minus 4 squared equals 16. Now you can't just start operating on this x because it's in parentheses that are being squared. So the first step here would be to do the inverse operation of this square. Well, the inverse operation of a sine is a sine inverse. So down here on the bottom on the right side, if you have the trig function on a theta, and that equals some value, well, what you should be doing is taking the inverse trig function to free up that theta. So the trig and the inverse trig function will cancel, leaving you with just theta equaling a trig to the -1, or a trig inverse of some value. And normally on any given calculator that has trigonometric operations on it, the only ones that will be available are sine, cosine, and tangent. There is no cosecant inverse, secant inverse, or cotangent inverse. So on the next slide, I will show you how to deal with that, as well as what happens when you're in radians. But for right now, we just need to take the sine inverse of both sides. So I'm going to write sine inverse of both sides. And so what this equation will end up looking like is theta equals sine inverse of 0.8225. So at this point, you will want to type this into a calculator. And after you type it in a calculator, you'll see that theta is 61.9 degrees. And you'll want to make sure here, I have this little thing in parentheses here, this reminder that your calculator is in degree mode. All right, so here in this other example, we have tangent theta equals 1.5214. So you may have guessed already that you want to take the tangent inverse of both sides, so that will look like this, the tangent inverse of -1.5214. And so again, you can type this into a calculator and get that theta is -56.7 degrees. But that doesn't make any sense. We want to make sure that that is in the first go around. And what I mean by that is somewhere between 0 and 360 degrees. So we add 360 degrees to this to put it in the first revolution of a circle, the first positive revolution of a circle. So when you add these two together, you will get 303.3 degrees. On this slide, the last one, you are asked to approximate to 1 decimal place in radians all thetas. So what you'll do here is notice first that this is not a sine, cosine, or tangent, and neither is this. So what we'll have to do instead is first rewrite the left side of this equation. So cosecant is 1 over sine, and this equals -2.3179. And that's fine, but now I still can't do anything with this sine until it's isolated. So if I multiply both sides by sine, I will get 1 equals negative 2.3179 sine of theta. And to isolate this theta, I will divide both sides by this negative value. So this will end up being 1 over negative 2.3179 equals sine theta. Once you have the equation in a form such that sine, cosine, or tangent is isolated, then you can go ahead and take the sine inverse. You can take the trig inverse of both sides. So this will be sine inverse of 1 over negative 2.3179 equals theta. And again, you just need to type this right into a calculator and get negative 0.44607 radians. Again, this is in radians this time. So no degree symbol here, just a number. But again, this doesn't make much sense to us because this is a negative angle. We want something that is in the first 2 pi. So if you approximate 2 pi to be 6.28318, and I'm picking 2 pi because that's how we find a coterminal angle. When you approximate 2 pi to be this value and you add these two things together, you will get 5.83711. But you are only asked for 1 decimal place, so you can round to 5.8 radians. And finally, with this last one, you can do it somewhat similarly, except cotangent becomes 1 over tangent theta equals 2.3810. And then when you solve for tangent of theta, you get 1 over 2.3810 equals tangent of theta. And then from there, you can take the tangent inverse of both sides, 1 over 2.3810 equaling theta. And then again, you can type that right into a calculator and get theta equaling 0.39762. But since we only need 1 decimal place, 0.4. Now, I've not talked about the other values that are used for this, right? So if you're finding a cosecant within the first 2 pi radians or the first full revolution, you will end up with 2 cosecant values or 2 angle values that give you a negative cosecant value. This is one of them. And for this answer over here, 0.4, or more specifically 0.39726 ... forever. This is not the only cotangent, the only angle that will give you a cotangent of 2.381, but it is one of them. And so that's all I'm interested in right now, is to have you find one. We will find the other ones using reference angles a little bit later. This concludes the review for the Precalculus first trig unit.